Okay, I'm Alan. I'm first-year graduate student from City Science Group. And yeah, I'm here to talk about AI, large language model, and agent-based modeling. So yeah, I will just make it as a project sharing, to show, what I did before I come here, what I did, yeah, it's just a project sharing. So the first section is mobility simulator, which is a project that we use agent-based modeling to do urban mobility simulations. And then the second section is Insight Navigator, which is a project that we use AI or language model to help to improve the citizen hotline system right now. Okay, so what's the motivations of simulating like urban mobility? So this is a usual situations that it happens every day in Taipei. So since that mobility is one of the key factors to impact human living quality, and then also contribute a lot of issues that are related to unsafe, street traffic congestions and carbon emissions. So to achieve the net zero 2050, comprehending urban mobility is very important, and then understand it and then minimize the carbon footprints are very essentials for every city. Yeah. So yeah, just like Parfait and Rui said, to achieve this kind of simulations, we use agent-based modeling. Agents mean the persons here. And so if we want to do this kind of simulation, we have to acquire massive individual data, where you live, where you work, and then where you go to eat, maybe. So collecting this kind of data is very sensitive, and maybe it's illegal. So how we solve this problem is that we use large language model to help us to synthesize synthetic population. So here there are two circles. So the left side is the real world, and then the right side is large language model, and then the intersection is our simulations. So the goal is that we want to use large language model or generative model to have a totally overlap together, to as real world data. Yeah. So yeah, first step. Profiling. So how can we generate people profile in the city? So we know that a lot of demographic data are recorded independently. So you will not have an age distribution, and then you know the correlation between age and then occupations. But in real world, we have that, right? So for example, if you are 3 years old, you can't get a PhD degree, right? This is the correlation. So how we did that? We use large language model to generate a correlation between this demographic data, and then use some optimization method to optimize this Bayesian network to generate realistic agent profile in the city. So yeah, this is a graph to show intuitively. So without the method that I mentioned, we will generate some people, some persons who is 3 years old but have already earned a PhD degree. But with the confinement of large language model, we can generate reasonable agents in the city. So before simulations, we have we generate agent profile, and then we use large language model to generate daily schedule for each agent, and then we have to match each activity into an actual point in the city, where the activity should happen in the city. So how we do that? We design stop points, which is living place for agents here. So we use income label, regional income distributions, and then residential distribution, and then their income to trying to find out where they should live in the city. And then frequent destination, which is workplace here for agents. So we use their occupation category, and then we crawl all the POI information from Google Map, and then we do some semantic mapping, to see, if you are a software engineer, you should work in tech company or a commercial company. Yeah, some less kind of semantic mapping. And then doing this kind of semantic mapping require large language model or language modeling. Okay. So occasional destinations. So here, this is a schedule. Take a break and eat lunch with colleague. This is a occasional schedule. And then we use the semantic of the activity, and then the POI information for each building, and then to try to map, and a half model to try to map, where this activity should happen in the city. So after mapping all the buildings into activity, we designed a multi-transit routing algorithm to calculate how agents move between their schedule. So yeah, here. So like we simulate 1,000 like agents in Taipei. So let me turn off it. Yeah, so let me run it. Okay, so this is an animation. It is a smooth animation, but due to some technical issue, it's not moved. Anyway, it's animation. So here, you can see there's an agent whose age is like 71 years old, and then the left side sees that this is the activity that's generated by large language model. And then here you can see the activity is like attend the Waters aerobic class at a local community center, and then it's a POI, face plan gym. It's an actual like buildings in Taipei right now. So like we designed the algorithm to find out how this activity interact with urban context or POI information. Yeah, so like we also like use the heat map mode. Oh, let me figure out. Okay, so here this is heat map route. So like, okay, let me try again. So like there's a time intervals here. So we calculate how agents move in this time period, and then aggregates all the paths together to form a heat map. So this is a route heat map. So like the lightest routes means that there are more agents moving on this road. And then the darkest means that there are less agents moving on, during this time interval. And then you can see like the left side calculates how many average distance they move, and then how much carbon emission they emitted. And then you can also use the filter, I only interested in how agents move by private vehicles in this time interval. So yeah, so like I think that's all for the demo. So this is just a platform that we are trying to simulate current mobility states in the city, but we develop all this modules step by step. So the next step of this project is actually we want to maybe we can use this platform to create a new bus route, and then we want to see how agents interact with this bus route, if it's an efficient transportation planning. So yeah, so it's a tool to help us to analyze new planning or policy. Yeah. Any question? No? Okay. So, second sections, Inside Navigator. So, do you know Citizen Hotline is a phone call that you can call to complain something to government. So citizen reports is a way to help us understand what citizen issues are happening in the city, but traditionally reports are classified or analyzed by people, which cannot fully reflect when the data gets larger and larger. The analysis will be more complex and more complex. So with the advance of language model, it's very good at semantic process. So we think AI can provide insights of some core issues that are complaining inside Citizen Hotline system. Yeah, just a casual flow to show you how we did it. So we collaborate with government. So we collect the reports data and then use the first AI technique, language embedding. It's like a technique to convert language into some high dimensional vector. So since it's high dimension vectors, so we can group the similar vector together. It's called clustering. And then we also use large language model to define each clustering topic. And visualizations, hyperspace, how do we visualize high dimensional data to help us understand the insights. And filtering, filtering is filtering, So this is just a first step of our project. So you can see we collect, there are 100,000 citizen complaints, I think. And then we use the technique I mentioned. And then, there are some main topic, environmental issue, infrastructure maintenance and safety, lighting and utility, animal welfare and control, some stuff like that. So this is just some case analysis. So this is actually visualized by district. So the blue is area 1, the green is area 2. So we want to find some insight, maybe there are some geographical distributions, inside your Citizen Hotline complaint. But we actually find some things. So like you can see, it's like green one happens like more complaints about like noise pollution or noise complaint. And then every one actually happens more about air quality. So yeah, so with this, we can like, understand, the geographical distribution of your citizen hotline complaint. So yeah, we actually build some interactive platforms that you can play to find some insight. So here, I think there are like 60,000. So the reason why it's 60,000 is that we don't have like enough computation on browser to visualize, thousands of data. So here, each dot is a complaint, and then like I say, we convert all the natural language into a high-dimensional vector, and then conduct clustering algorithm to find a topic. So the left side is the 20 topics that we find out. So you can see the street light maintenance is the most popular issue that citizens are complaining about. And then you can also like use the responsible agency, to see, which agencies should be responsible for those complaints. And then we also build some search engine, search function. Like, sorry, it's Mandarin because the raw data is Mandarin, but yeah. So right now, it is doing searching. So here, this is the search results. They are related to traffic jam. Okay. So you can see traffic jams, the popular topics, public safety, traffic signal issue, and road maintenance. And you can also click the map. Wait, why is it? So this is the geographical like points for each complaint. So you can see it happens a lot in downtown, which is here. This is Kaohsiung, by the way. This is Kaohsiung. And then less happens on countryside. So with this, so like you didn't understand what's going on inside this like complaint, right? So we also designed the graph mode to like, models these like complaints into the graph. So you see the dots here you see is complaint, and then the link is the similarity between complaint, because we can like convert complaints into vectors, so we can calculate similarity between vector. So click it. So this is a function that we use AI and some like graph algorithms, like community detections algorithm. You can just take it like a graph clustering. So there are 4 groups right now here. And then they are all related to traffic jams. So what it did is that it helps you to find out the topic inside your search result. So traffic jam, you can see there are sounds like here. Wait, let me change the color. Yeah, okay. So this is sounds like payments and some like road safety. Like I think most people complain about like there are some pothole, on the road, and then maybe it reduces the speed of the car, so it may cause traffic jam. And then signal problem improve, traffic signal is broken, so maybe it may cause traffic jam. And then road constructions, makes sense. And then idling, like there are some, idling vehicle. So this is just a platform to help government, to navigate issues by citizen hotline. So this resource can show government, if they want to solve the problem about traffic jams, maybe they can start from this 4 topic. Okay. Do I still have time? Yeah, so I have some, maybe most of you guys are curious about the accuracies of the agent-based modeling. I have some validation. So this is like the demographics. So like the agent profile I mentioned. So this is actually the accuracies. So it's pretty accurate, but it should be accurate because we sample in data from Guangqiu's, from the collecting demographic data. But yeah, we just do some technique, to like consider the correlation between demographic. Yeah. So we have transactions history data, in Taipei, so we can like calculate how many people actually come out from the metro stations or go into the metro station. So here, the dot lines is our simulations, and then this is Guangqiu's. Okay, it looks accurate, maybe, but it's not accurate if you use some quantified indicator to see it. Okay. So actually, we think ours like urban mobility simulation is like an iterative process. We have to iterate it a lot, to increase the accuracy. So here, this is a comparison between Guangqiu's and simulation 1.0, which is the first simulation we did before. And then this is telecom data. This is telecom data. And then this is our simulations. So different, right? So we use sounds like more data to calibrate our simulations. Look more similar, probably, yeah. So yeah, this is the routing validation. Because inside the routing module, we have to define what mobility mode the agents will use. Actually, we just use shortest time path or shortest path, as a mobility choice. So you see here, in real world, there are more people taking metro. In simulations, there are less people taking subway. Yeah. This is a video. This is a timestamp video, but I think we are good. Okay, any question? Yeah.
Cool stuff. So I remember you were saying like most of these tools I use when you do simulation just to like study existing conditions. How hard is it to like actually produce something that's very generative in the sense that you could, like you said, add a bus route and see how agents react to it? Like how hard is the implementation for that?
Oh, how hard is the implementation for that? Yeah, I think there's no like limitation for that. I think we can do it, yeah, maybe in 3 months. But yeah, I think the hardest part is the computation platform. Yeah, because you have to calculate 1,000 routings. If an agent has like 3 routings a day, 1,000, there are 300,000 routings you have to calculate. Yeah. So right now it's like offline simulations. It's not online simulation. Online simulation is that maybe I correct one agent profile, or maybe I correct, I modify MIT into commercial building, and then I want to see what's happening inside the simulation. That's called online simulation. But we are not that right now. Yeah.
I'm wondering what are the factors that cause this gap between the real world data and also the outcome from simulation. Are the input data really factoring what makes a difference, or it's just
Yeah, I think that's a good problem. So that's a good question. So yeah, we actually want to standardize the input of our systems. So for example, you just need age distribution, income distribution, and some stuff like that, and then you can have a perfect simulation. But the problem we met before is that it's pretty hard to really standardize this stuff because in every city they have different data sets. So right now we are just when we get new data set, and then we see it's a good quality data, and then we can calibrate our model. Yeah, some stuff like that. Yeah. And then only thing you can validate is validation here. Yeah. Good.